Hello guys, my name is Kartik Joshi, and this is my research topic on multi-agent systems for software vulnerability detection. I'm from UT Dallas, and let's begin. So this is the roadmap of what I'm going to be talking about in my presentation. So I'm going to start with talking about vulnerability detection. Then I'll go into talking about LLMs and LLM-based agents. Then I'll talk about the previous frameworks which are used to try to detect software vulnerabilities. After that, I'm going to talk about my proposed approach and how that compares to the previous frameworks. And then I'm going to show you the preliminary evaluation and my next steps. So, what is vulnerability detection? So, in short, vulnerability detection is the process of identifying flaws in software which can be exploited by attackers. These type of vulnerabilities include buffer overflows, SQL injection, cross-site scripting, reentrancy, and API misuse. So, a lot of times hackers or people who are trying to exploit a website will use these and inject them into your website for a certain task. And what is a large language model? So we've all heard of ChatGPT and Gemini and all these models. A large language model basically is a deep neural network trained on massive textual data. Like we're talking billions of data sets and really massive data sets. And they're kind of trained to generate human-like language responses. And they're based on the transformer architecture, which means that they have self mechanisms to capture relationships. And there's three main type of architectures for this. We have encoders, which are like your BERT models, so for classification and understanding and for embeddings. We have the decoder, which is for text generation, so your ChatGPT and other standard models. And then you've got the encoder decoder, which is for translation and summarization, like T5. So an LLM-based agent, what it is you give the LLM the ability to plan, act, use tools, and remember conversations. So you can sort of think as the LLM as being the brain, and it has a bunch of these things it can do to give a more accurate response. So a good example of this would be GPT, which came out with their agent mode, where you can use it to buy Uber or DoorDash. That would be an agent because the LM acts as a brain, but it has all these other abilities like planning, memory, perception, and action. And the action is the most important step in this entire thing, where you have a toolkit. So you have a bunch of tools you can use, such as you can have API calls or you can connect it to a database like a RAG, etc., etc. A little bit more about LLM-based agents. So, like I mentioned, the LLM serves as the brain and it possesses decision-making and planning abilities. And the model, the good thing about LLM-based agents is it can handle multiple interactions and maintain a contextual understanding. And on the right, you can kind of see an example of this. So in your plain LLM, you have a user who prompts something and it goes to the chatbot where it generates a response. And then us, the user, can decide whether we want to accept it or we want to reject it. And then we have to again reprompt it until we think it's self-sufficient. And then we get a final refined version. On the other hand, LLM-based agents, the way they work is you have separate agents who are capable of doing separate tasks. So in this case, you have two agents, a product owner agent and a requirement engineer agent. And both of them have specific different tasks they can do. So as you can see, there's a role description and a task for both of them. So they know exactly what they can do and they won't do anything else besides that. And they kind of work in sync with each other in circular loops, and you get a more refined version as a final response without having to reprompt it and reprompt it over and over again until you get a good response. Um, Talking a little bit more about single agent versus multi-agent systems. So single agent systems struggle with handling entire task pipelines, and they are very prone to hallucination because the context window right now is 128K or 258K tokens, and a lot of the times it can go further than that. Sometimes prompt engineering can help with this. So when you specifically prompt it to give a specific type of response, but even then, it does have tendencies to hallucinate. Multi-agent systems do a good job with this because they have multiple LLM-based agents, which each have a specific role. So you have a developer, you have a reviewer, etc. So you have specific roles for each of them. And like I mentioned in the previous example, you can collaborate amongst these agents in circular loops, or there's other ways of collaborating, like you have tree collaboration where you can branch out from one agent. And then, like I mentioned, there's tool integration. So you can use external sources, you can call APIs, etc. And the easiest way to think about this is, when you go to Gemini and you ask it, hey, what's my name? It doesn't really have tool integration, right? It can't answer that question because it doesn't know your name until you tell it to. But if you had, like, let's say an API call to your Gmail where it knows your name, then you can get your name from it. So that's what multi-agent systems are good for. And so now talking about back to our question. So what we're trying to do is solve the issue of code vulnerability in we're trying to solve code vulnerability issues and using LLMs for that. So one of the original works is GPT Lens. What GPT Lens basically is it's a two-agent system which can be used to detect code vulnerabilities. And so there's two steps. The first step, we have our auditor agent. The auditor agent's job is to analyze your code. So in this example, it's a smart contract, which is a blockchain contract, blockchain code base, and you analyze it from different perspectives you cast a wide range of potential vulnerabilities. And then after you cast that wide range of potential vulnerabilities, you go to stage two, where there's a critique agent where it serves as the critique, reviewing the full list of vulnerabilities, and then ranking them and giving you a response on the vulnerabilities for each. The problem with GPT Lens, however, is it doesn't really have reasoning. What I mean by that is it's simply just trained on GPT-4's database, and it doesn't think. It just, whatever it knows, it will respond with that. And it also does not have inter-procedural analysis. So what this means is that if there's a function which calls another function, and the function it calls has an error inside of it, like a code vulnerability, it's not able to jump over those method calls and go deep into the internal trace. And that's not good, because we want this to be as accurate as possible. And the goal we're trying to solve is to try to convert GPT Lens into a proper multi-agent React system. And I'll talk a little bit more about React upcoming. So another previous work is Voltrial. So Voltrial is more in the domain of what my proposed framework is. So Voltrial has a multi-agent framework that employs a courtroom-inspired scenario. So it tries to mimic a courtroom in the way it detects the vulnerabilities. There's four specific agents. You have your security researcher, code author, moderator, and review board. And I'll talk about them in the next slide. So what this is so you start off with the security researcher. So let's say you have code file which has a vulnerability, or you're trying to detect a vulnerability. You pass that file into the security researcher. The security researcher's goal is to try to detect the vulnerabilities. So it's similar to the auditor agent in GPT Lens, where you're trying to detect what vulnerabilities exist. After it detects what vulnerabilities exist, it moves on to the code author agent. So the second step, the code author's job is, instead of trying to rank it, it is to try to disprove the findings of security researcher. So you're seeing kind of two sides. So this can be like your defendant, or the person trying to defend a claim, and this can be the person who's not trying to defend the claim. So they're both kind of bringing up their points, and then they both disagree with each other. It goes to the moderator, where the moderator takes the output from the security research and the output from the code author, and it gives its own take on it and what it believes the truth is. And this can happen for as many rounds as you want. So you can make this go for 10 rounds. Like you can see, this is like a circular loop. So it can go into custom rounds, like 10 rounds, 30 rounds, 50 rounds. But obviously, the more rounds it goes, the more money you'd spend on API calls. And then finally, after those rounds, it goes into the review board, where the final verdict is made. So after all three of these initial agents give a response, we move on to the final verdict, where it can then give its own response based on whatever the claims of these other agents is. And this is a more refined framework compared to GPT Lens, because it's agentic, it's multi-agentic, And it also, you can instruction tune specific agents for more accuracy. And the final previous work, which we need to talk about before I mention my approach, is JITWL. So JITWL is a data set which is used for benchmarking and evaluating these frameworks. So like I mentioned, a lot of the previous frameworks like Primeville, they didn't really have a lot of examples of multi-hop functions or interprocedural analysis. And JITWL solves this by creating a pairwise benchmark where you have two versions of a code file. You have the vulnerable version and you have the benign version, which is a not vulnerable version. And then you have a pairwise evaluation where you can then see how accurate your framework is in kind of finding more complex and detailed vulnerabilities, because there's not a lot of difference between the benign and vulnerable version of a code base. It really requires you to reason and think. And also, like I mentioned, these previous frameworks or these previous data sets for evaluating these frameworks, they did not have multi-hop functions. So like they didn't have a function call inside a function call, which could be vulnerable. But JITWL does that, so it's more accurate. And this is a little bit about how the JITWL dataset was created. Um, you can see over here, it has 879 of the most common vulnerabilities from Primeville, which is a previous dataset. And then what they do is they go through the GitHub repositories and they find the commit where it becomes B9, and from there they extract that function, which was B9, and then they backtrack it so they can find where the vulnerability was introduced. So they create a function pair where there's a B9 and a vulnerable version of the same thing, which then can be used for testing. And since there's 879 entries, there's actually 1,758 actual functions to evaluate, because there's a B9 and vulnerable version of each function. Okay, so now as we get into our framework, another concept which needs to be known is React, which refers to reasoning plus action. What React is basically it prompts LLMs to generate verbal reasoning traces and actions for a task. And this allows the system to perform dynamic reasoning. So you can see on the right, in this top right, you have a target function which goes in. And from here, it goes into the React part where it thinks. So it thinks that it needs to call, it looks at the function and it says, I need to look into the callers of the functions, which basic callers means what functions that function calls. And once it thinks about that, it goes into the action step where it invokes these tools it has. So you have these tools over here, like we mentioned. It has get callers, which what it does is that it finds the methods inside of a method. Get callees, which refers to what methods call the method you're currently in, and get definition, which just gives a definition of what that method does. And after the action, it goes into observation, where it can then either go back in that loop, or if it thinks that it's got enough result, it can go into the prediction stage. So on the bottom right, you can see a sort of skeleton of what it looks like. You have a sort of like skeleton of what it looks like. You have the tool calls. You prompt engineer a little bit so it follows that same output formula. And then on the left, bottom left, you can see an example of this in action. So you think, you act, and then you observe. And then in this case, so you need to search Apple Remote and find the program it was originally designed to interact with. So after you think about that, your action would obviously be to search up Apple Remote. So you'd probably connect it to a Google Search API or something. And then after the action, it goes into the observation where you get the result from the action. And then it goes back again in a loop. So that was one trace. Then it goes into another trace, and finally the fourth trace. And this is more examples of the difference between using plain LLM versus a React agent. So on the right hand side, I'll talk about that first. So you have a vulnerable response, which is correct. So the plain LLM did give an accurate response here, and so did the React agent. But you can see the React agent goes a lot more into detail and depth compared to the plain LLM response. And you can see its entire reasoning trace, the action, thought, action, thought, observation, that entire trace. And on the right hand side, you can see that in this case, a plain LLM response actually classified it incorrectly. So it thinks it's vulnerable. However, it's actually not vulnerable, as you can see in the bottom. The right answer is that it's not vulnerable. And you can see that because the plain LLM didn't have these tools and this reasoning, it goes off of whatever it can see in the function, but it doesn't know that there can be another function calling it or something happening behind the scenes. And the React agent is good for that. And on the left hand side is sort of a for evaluation. You have simple vanilla prompting, which is just you ask a model like do this for me. And then you have few shot examples where before you ask your question, you give it a few examples so that it's more in tune with it. And you have chain of thought where you just tell the model to solve this step by step and show its reasoning trace and how it arrived there. And this chain of thought should not be confused with React because this is just chain of thought can be just thought of as simple prompt engineering and fine tuning the prompt compared to React, which is a framework. Okay, so the short and abstract of what we're trying to do is software vulnerability is a critical task for ensuring secure systems, yet it remains challenging. And single agent LLMs suffer from incomplete reasoning and unchecked errors. And that's why we proposed a new multi agent framework, which builds upon the previous frameworks of GPT Lens and Voltrial, where we have a React based agent, a critique agent, which is similar to the critique agent from GPT Lens, and an evaluation agent, which compares against the ground truth and just tells us how accurate our response was. So this is the proposed approach I have. You have a React agent where the process begins with the React agent examining the code file. After that, it goes into the critique agent, which you can see over here, which takes in the output from React and critically reviews it. From there, it goes into the evaluation agent, which is only used for comparing ground truth. So the evaluation agent can kind of just be thought as just like once you get your final response, you want to see whether our thing was actually accurate. So if we said that a code file is vulnerable, but in the JITWO dataset, which we're going to compare against, is actually not vulnerable, we need to evaluate, we need to see whether we got it right. And so we can see our final results. And if it's correct, it confirms that vulnerability. However, if it's incorrect, it learns from that vulnerability so that it becomes better over and over as it sees more examples. And between the React agent and critique agent, similar to Voltrial, if they disagree, so if the React agent thinks it's vulnerable, but the critique agent thinks it's not vulnerable, and they disagree, they go in a circular loop until they both come to the same response because we don't want two different responses. Okay, so this is a breakdown of how it works. You have your system input. In this case, this is probably the smallest function we're checking. There's bigger functions, but you see a system input here. It can be a file or a method. And in this case, it's a method. And this is sort of what we're going to be checking for a vulnerability. From there, the system input goes into the React agent where it begins a cycle of thought, action, and observation. And in the action step, it has the ability to call tools like getCaller, getCallies, and getFunctionBody. And for that, we use LangChain. And we're gonna pivot to LangGraph, but for now, we thought LangChain made the most sense. And the output of the React agent is a binary decision. So you either get that it's vulnerable or it's not vulnerable. And you can see on the bottom is kind of a very small reasoning trace. So you can see it goes to the function, it sees general vulnerabilities, it gives it a score, and then you can see it calls an action, get function body, and there's obviously a lot more reasoning trace, but I couldn't fit it in here. And then after the React agent, it goes into the critique agent, which has a role of validating and refining the findings of the React agent. So it will take the output from the React agent as well as the code base and then provide its own independent results. And you can see in the bottom, it's providing its own results. And if it does not agree with the React agent, then it prompts a circular loop where they both go in a loop until they both come to the same response. And then you also, one thing we noticed while testing this out is when you tell the agent to give a score for how probable the vulnerability is, it's more accurate in giving the right result. And finally, the evaluation agent, which we're currently building out, has reflection in it, which basically means reflection refers to self-learning ability, which can be used for learning and giving more accurate data findings. But that part is being built out, but obviously the part where we compare our results is there. And so here's our preliminary evaluation. We ran our framework against against GPT-Lens and Voltrile on 50 samples from the JITWO dataset. And you can see it ran a pairwise function, so one vulnerable version and one benign version. And because we were running a pairwise, we were evaluating it against a pairwise dataset. We wanted to use false positives and false negatives because it makes the most sense. Because we don't want to get false positives and false negatives in these benign and vulnerable methods. And you can see over here that our framework, so GPT Lens got 40% accuracy with 15 false positives and 15 false negatives. Voltrial got 48% with 17 false positives and 9 false negatives. Our framework, which with only one agent, so when we only used the React agent, got 50% accuracy with 10 false positives and 15 false negatives. And our framework, when we used both agents, so we used the React and the Critique agent, we got 60% accuracy and 13 false positives and 7 false negatives. And you can see on the left what the results look like. So there was 50 cases we analyzed against. There were 25 vulnerable versions and 25 non-vulnerable. And the average debate round lasted 1.2, which basically means on average, the critique and React agent disagreed once and then went in a loop once, like 1.2 times. So really they didn't disagree that much, but a few times they disagreed. And you can see at the bottom, in one round, it resolved 38 cases, and in 2 rounds, it resolved 12 cases. So the next step now is we want to finish evaluating Voltrial on the big framework, and we already finished evaluating GPT Lens on that framework on the 1758 JITWO framework with 1758 the data sets. So GPT Lens got 50.17% accuracy. The next steps would be to evaluate this on the volatile framework and then evaluate it on our framework and then compare and see which one is the most accurate. And another thing we want to do is we want to get all the intermediate steps for each of these frameworks. So what I mean by this is instead of just classifying whether the response was correct, so whether we got vulnerable and the result is vulnerable, we also want to classify whether the description of the vulnerability is accurate. So let's say that we get a response that is vulnerable with a cross-site scripting vulnerability. However, the real vulnerability is an API misuse. Then we want to also be able to compare the errors so it can be more accurate because it's not really accurate if it only gets the vulnerability, the binary decision right, and not the actual error. And yeah, so that's something we want to do. We also want to test it on few shot prompting, so giving it a few examples and seeing how that would impact it. And yeah, I'm excited to continue. And thank you.